Oh, this camera thing drives me. Let's see. Hopefully this will work. Give me 1 second. I'm gonna do two things. I'm gonna shut this email off. And then why this thing's so messed up. Let me share the screen too. Are you seeing something that's like a camera coming up right now? Everybody? Can you see my yellow pad or not?
We're just seeing your desktop, your computer.
You're not seeing the yellow pad though? All right, hold on. Let me try it again. Sorry, I think this will. Can you see the yellow pad now?
Yes.
Okay. All right. I'm going to go ahead and go through quarter wave matching. And this is a technique used all the time when you're fabricating things on a microchip or on a chip itself. And I'll explain this in a little bit. So this is quarter wave. It's called impedance matching or matching. Just follow me on this and you'll be okay. Make sure you go through this too. Quarter wave matching. And here's what it amounts to. If I go ahead, give me 1 second. Whenever I share a screen, it collapses down the viewing, and I can only see a few of you, so I open it up. So quarter wave matching means the line's length is a quarter wavelength long. Now this only works at one frequency, and it's important you remember that. So we're going to have a characteristic impedance. Instead of Z naught, we call this ZS, and the thing we're going to design for is the value of ZS. And then we're going to assume the load has just a real component, not an imaginary. This will not work with an imaginary load. So I'll just put R load here. And that's going to be the load impedance. Now, it's the typical coordinate system. This will be the Z-axis. This will be at 0. And the length of this line, L, will be equal to lambda over 4, or quarter wave. Now, this is coming from a transmission line that has a characteristic impedance of Z naught. And what we want to do is make sure that the input impedance right here, Zn, is equal to Z naught. Now, I think everybody knows that the input impedance to that line is Z naught, the reflection coefficient will be 0, correct, class? If this is the case, then necessarily the reflection coefficient equals 0, and that's what we want. All the power and all the signal will be transmitted into the load, R load. This is the load. Everybody understand that, class? With me? Okay. So first thing is, what is the equation for the input impedance into a transmission line? Well, the Zn here generally, just watch this. Zn is equal to, it's the characteristic impedance of the line. Now it's not Z naught, it's ZS, because this is the transmission line we're talking about. So it's ZS, right? And then it's going to be times the load impedance. Well, the load impedance is just RL, it's strict real, plus J, and then it's ZS, times the tangent of beta L, and L is the length of the line, over ZS plus JRS times the tangent of beta L. And I just rewrote the input impedance equation. I replaced Z naught with ZS and Z load with RL. It's strictly real. Can everybody see this okay? You got me? All right, now, the key thing is this argument, beta L. So will be equal to, beta is equal to 2 pi over lambda. Does everybody agree with that, class? Beta is 2 pi over lambda times L. Well, the length is lambda over 4. So this quantity becomes pi over 2. I want everybody to see that. Do you all agree with me there? Now, the next thing is, what is the value of the tangent of pi over 2? It's the same thing as tangent of 90 degrees. And what is that value? Anyone?
It's 1.
It's infinite, isn't it? Right? I want you to think about what the tangent is. It's the tangent of an angle. If this is an angle, right? And this is y and this is x. The tangent of that angle, tan of theta, is actually equal to y over x, right? Isn't that right, class? It's opposite over adjacent, right? Everybody? At least acknowledge you understand that about the tangent. It's always the ratio of opposite over adjacent side if it's a right triangle. And this is assuming a right triangle. And if this angle goes to 90 degrees, can you see that the ratio of y to x goes to infinity? Everybody? With me on that? How many see that? I'm trying to make it as visually clear as possible. All right, now what happens really is this. This quantity right here is tending to infinity, and this quantity is tending to infinity. That's supposed to be ZS. You all see this? I mean, sorry, that's supposed to be RL, my bad. This is supposed to be RL. I don't know why it didn't show up. Now, if these two quantities are becoming enormous, this quantity and this quantity become inconsequential. They're negligibly small. So I can actually say that Zn here, when it's a quarter wavelength long, will be equal to simply Zs squared. The tangents will divide out, divided by the actual load impedance, or RL. Can you all see that? Now, if the line is a quarter wavelength long, necessarily the tangent is tending to infinity. So the RL and Zs over here become inconsequential. The J's cancel out. And I have Zs squared divided by RL. How many see that? With me? Now, we're designing for Zs. This is something we can do. So we calculate what Zs is. And Zs is simply the square root of Zn, or I should say here, we want Zn to be Z naught now, right? We want this quantity right here, the input impedance, to be Z naught, so we get a reflection coefficient at 0. Y'all follow me on this, class? So now we make this Zn equal to Z naught. So Z naught times RL, the square root of that, will be the impedance. And that's called quarter wave matching. That's the basic principle that dictates it. Now I'm going to mention what that comes up, what happens when we realize this, what really happens. Here's how it's done. You know, transmission lines are any two conductors, right, that are separated and insulated from each other, and they run in parallel, but there's no change in the cross-sectional area. Like a transmission line we talked about was a coax cable, coaxial cable, two twin lines, right? Another very, very common transmission line is called a coplanar waveguide, and these are fabricated on circuits. And what it is this. You're going to have something where you have, typically you're going to have a doped silicon. Have you all had your class that talks about silicon and how you can dope it and make it a conductor, right? Then you grow an oxide on it, so there'll be an oxide on it. And then you delineate a pattern. I'm not going to spend a lot of time on this, but you're going to have some silicon dioxide right here. Silicon dioxide. This is not important. You understand how to fab it, but this has to do with masking and photolithography that you're going to get in another class. Have you had your microelectronic lab yet or anything like that? If you've had this, you know about masking, you know about the acid wash and stuff like this, where you delineate a pattern. And then on top of this, there's going to be metal right here. Well, between this metal and this silicon is a transmission line. And we can control the impedance of this transmission line by dictating the width and the height. And now I'm not going to ask you to get into this now. This comes later, but I want to just tell you the way we actually deal with changing the impedance of a quarter wavelength line is by the ratio of width to height. and also of the material. Silicon dioxide has a certain epsilon relative. That's just some information. That's how we're going to build these things. Now, quarter wave matching, and this is critical, since the length of that line is a quarter wavelength, that only works at one frequency and just a small amount of bandwidth. So quarter wave matching does not work for signals that are like digital, where you get a spike like this and it goes down. This only works for steady state, something that varies at a constant frequency. Does everybody understand that, class? Something else I'm going to mention, all the matching that we're doing here in general, the impedance matching, only works when you're talking about a constant frequency. If there's a wide difference in frequency, say the center frequency of the signal moves like 30%, then all this impedance matching won't work. It has to be a frequency that has very little change in the center frequency. And that's something you need to be aware of, because more and more these days, we're talking about things that are at wide band. They have a lot of frequency components, and you can't use this for impedance matching that. Okay, I wanted to cover that first. And now I think, how many people do we have on here right now? I can't see myself.
There's 10 people on right now.
Minus me?
I think including you.
Okay, so there's 9. I think we have more than that in the class. A few people aren't on. But that's typical, though. People have things to do, or they slept in or something like that. But hopefully everybody will get on board in a bit. Now, I want to answer any questions you have about the homework. Our homework was based on matching with a series or a shunt element, right? Either a capacitor or an inductor, right? Does anybody have any questions about the homework? I want to go through at least one of the problems. And you all have compasses now, right? And straight edge? Well, you want to choose a problem for me? I like giving you that option. Let me go ahead and get that up here.
Professor,
Yep.
this isn't actually like one of the problems that was about matching too much, but at the bottom it said do problem 2.31.
Uh-huh.
And I was a little bit lost on that one.
Well, let me take a look. I'm going to make sure everybody can see this before I take off on it. In figure 2.56 is generated for a 50 ohm slotted coax airline terminated in a short circuit and then an unknown load. Determine the measurement frequency, the VISWAR, and the load when the load is attached and the load impedance. Okay, this is what he's talking about here. Y'all see this right here, class? I mean, I want to make sure y'all can see figure 2.56. How many have books with you? Just show of hands. How many? Open your books to page 110 and just look in your book. Now, Whitworth's book does not explain this in great deal, but I'm going to show you something. What this is, what he's showing you here is the voltage on the transmission line versus position in centimeters. Can everybody see that? Here's the problem. It's a bit deceptive. Usually you put the load at Z equals 0, right? That's where all the theoretical work begins. We assume the load at 0, correct? But if you don't know where the load is exactly, the way you always get it is you replace the load with a short circuit. This is what you do in a laboratory. You put a short circuit on the load. And you know one thing, when you put a short circuit on the load, the voltage is 0. Do you all agree with that? So if this is the voltage magnitude on the line, then this point right here would be equal to where the load is. Can you all see that? Now, the next thing I want to tell you, I can't get the exact number, but it's not right on 1 and it's not right on 2. It's something you're going to have to interpolate. You all see that? Now, the next thing you have is you have a distance from here, from null to null. Now, from null to null is exactly half a wavelength. It's like going around the transmission line one time, 360 degrees, you go one wavelength. Everything repeats. So the distance from here to here is going to be lambda over 2. Y'all see that? I'm writing in my book. I probably should have done that before. Y'all see it, class? All right, now if that's lambda over 2, can you estimate this? If I had a good measuring device, I wish I had my ruler here, but I don't. But if you can see, it's like what? It's about 7.5 centimeters, isn't it? Can you estimate that on yours? Y'all getting about 7.5? Take a look, centimeters, right? Just look at the scale in the bottom and kind of shift it over a little. I'm getting about 7.5 centimeters.
It should be like 6.5 or so, shouldn't it?
Oh, I'm sorry. You're right. I'm thinking I'm at 0. You're right. 6.5 centimeters. How many are seeing that? My bad. You're right. Now, if it's 6.5 centimeters, then what happens? Well, I know I have lambda. And is that air-filled, by the way? Airline. So it's in air, so the velocity is the speed of light. So I know lambda is equal to 6.5 centimeters or 0.065 meters. Correct, everyone? And what is lambda? Well, wavelength is always what? It's always the phase velocity over f if we're lossless. We could actually, I mean, we could go through the proof on this for a lossy line and just see how it actually defaults that. But since it's an air-filled line, this becomes the velocity of light over f, or it's c over f, and we want f. So if you take a look at this, if this equals lambda and we want f, f is equal to c over lambda. So it's 3 times 10 to the 8th meters per second divided by a wavelength of 0.065. And what is that going to be? Anyone? Anyone? Y'all? Okay. I'm assuming you have calculators right there. I'll do it. I got to pull up MathCAD right here. So
I got 4.6 times 10 to the 9th.
I think that's right. I'm going to go with that. 4.6 times 10 to the 9th, or 4.6 gigahertz, right? I'll call it gigahertz. Do y'all agree with that? Now, the next thing with that question, what does it ask? They say, now they replace the load, or replace it with the load, right? Y'all see that? And when you do, what do you know? Well, here, I'm going to show you something. When I come into a transmission line like this, and let me do it this way. I'll come back to that in a second, but when I look at this, I got to get my camera back up. When I look at this, y'all see once the load is attached, that the ratio of the maximum, oops, sorry, I don't know what happened to my camera. The ratio of the maximum value of voltage to the minimum value of voltage would be the standing wave, would be the voltage standing wave ratio, correct, class? Vmax over Vmin, right? The maximum is about 4 and the minimum is about 2. Do you agree with that, class? So we get a voltage standing wave ratio of simply 4 over 2, or we get 2, right? Agreed, everyone? Y'all see that? Now, what is that? The voltage standing wave ratio, 2, is equal to 1 minus the magnitude of, 1 plus the magnitude of gamma over 1 minus the magnitude of the reflection coefficient, right? The load class, right? And if we wanted to get the reflection coefficient, what would it be? Well, I could multiply both sides. I'll just call this SWR, and I'll show you. if I take SWR and I take 1 minus the magnitude of gamma L, it would be equal to 1 plus the magnitude of gamma L, right? And therefore, I can keep going on this one. I can take SWR times gamma L with a minus sign to the other side, and then I have gamma L here plus SWR times magnitude of gamma L. And I can take the 1 to the other side, and here I have standing wave ratio, right? Minus 1. And then I can factor out 1 plus standing wave ratio. I can factor out gamma L here, and I have 1 plus the standing wave ratio is equal to standing wave ratio minus 1, right? I'm doing inverse problem. Do you agree with this?
Professor, can you switch
Oh,
to the document
God.
camera?
I don't know why that thing, it just shut, I think it shuts off on me sometimes. Do you all see it, class? What I'm trying to do is here, I say the VSWR is 2. First, do we agree with that? Right? You all can see it's the ratio of 4 to 2, correct? Now, if we have that, I'm going to calculate what gamma L is. So I know that the VSWR is 1 plus the magnitude of gamma L over 1 minus the magnitude of gamma L. So I'm going to multiply both sides by 1 minus gamma L. So I put SWR times 1 minus gamma L is equal to 1 plus gamma L in assumed magnitude. And then I do a little factoring and I get this. And finally, I get the magnitude of gamma L is equal to SWR minus 1 over SWR plus 1. Or in my case, I have what? 2 minus 1 over 2 plus 1 or 3. Or this is really going to be 1/3. You all see that? And that's the magnitude of gamma L. Correct? Now, here's what happens next. And here's where I'm going to make use of the Smith chart. Now I'm bringing my Smith chart back. And I come here. And I get my compass. There's probably several ways to do this. But one thing I know is that if the reflection coefficient is 1/3, right, then the radius here will be 1/3 the radius of the circle. And I'm trying to do this down here so you see it. You could do it, the standing wave ratio is 2. Right here is 2, right? Can you all, if you look on my thing and you look on yours, you have 2 there. And this is 1, or I can get, I could use a reflection coefficient. It won't matter what, but here's what I'm going to do to show you how to get this. I come down here, I'm going to use the VSWR of 2. And what I do is measure this, because this is the magnitude of gamma L. I'm sorry, this will give me the magnitude of gamma L on there. And then I come here. Trying to make this circle. You can do it with me if you have a Smith chart. Now remember, this is where it intersects. This is the standing wave ratio, right? Are you with me, class? Where the actual circle after the normalized impedance is taken care of, that's where it intersects this point. That is the VSWR from here to here, or standing wave ratio. Do you agree with me, class? How many understand that, right? You're getting familiar with the Smith chart, just do it. Now, what else do you know about this point? Well, this point is where there's a voltage maximum, right? V max occurs there at that point. Now, I want you to catch up with me, and I'm going to show you how to derive or come to terms with this and get the answer. Go ahead and draw it up. You ready? I see a couple people still working. You go ahead and draw that circle as best you can. Got it? Okay. Now, I'm bringing this book back and I'm showing you something. You can see that we replaced the short with the load right here. Y'all follow me? This is the line right here, the darker one is the one that shows you the magnitude of the voltage on the line versus position. Now, right here is where the load is, right? But we know a voltage maximum always occurs at the point where you cross right here, right? On this side, where this, no matter where the load is, when I cross there, I'm literally at this point on the Smith chart. Correct, class? And I know a voltage minimum occurs here. This is V min.
Your camera shut off again.
Camera.
I don't know why, but it's got a mind of its own, I guess. Thank you. So if you take a look at this, this is the minimum voltage right here, and this is the maximum voltage right here. We don't know where we came in. We just know that that's minimum and that's maximum, right? As you move away. If you're at, say, if this is where the load would be, the normalized load, as I'm moving, when I go through there, the voltage maximum occurs. When I go through here, a voltage minimum. And I'm assuming I'm at the load and I'm moving away from the load towards the generator. Now, I'm going to tell you one thing. Look at this now, right here. There's a voltage minimum that occurs about, what, 1.9 right there. Can you all see that? How many see that right there in your book? It's about 1.9. And again, I'm estimating. I wish Wentworth would have put a more, I guess, resolved graph, but he didn't. So this is about, the voltage minimum is about 1.9, right? And now I have to move, maybe it's 1.8. Can anybody get a better idea of where that is? 1.9 to 1.8 centimeters, right? If that's 1, it's about 1.9 to 1.8, right? Where the minimum is. Can you all see that? And it's not a sharp, it's sort of a gradual kind of it bottoms out, you know, slowly. It's not a real sharp one. But it's about 1.8, and you can see where the load is 1.1. So if you take 1.8 minus 1.1, you get 0.7 centimeters, don't you? Right? How many see that? Right? 0.7 centimeters. Now, I'm going to show you what to do with this one. I know if I'm at a voltage minimum, I'm right here, right? Correct, class? But now I'm not going away from the load. If I'm going towards the load, this way would be going towards the load. And I need to figure out how far I go before I hit the load. And I've told you, distance-wise, I start here at about 1.8, and I move to about 1.1, or I move 0.7 centimeters, right? I got to figure out how many wavelengths that is. Now, bear with me. So how many wavelengths is that? Well, if I know I have a wavelength, we figured this out a second ago, was equal to 0. Or really, it was equal to 6.5 centimeters, right? That's what our wavelength was. We looked, right?
Was our wavelength equal to 6.5 or half a wavelength equal to 6.5?
Oh, goodness. You are right. So we actually, I'm sorry about that. You're absolutely right. That's lambda over 2. So lambda should actually be equal to, I made a mistake here. Lambda here should be equal to 2 times 0.065 centimeters. And that's going to be 0.130 centimeters, right? Class? And if that's the case, I'm sorry about that. Thank you for catching that mistake. So this is not true. This is equal to, wavelength is equal to 0.1, not centimeters, meters, 0.130 or 13 centimeters. Now, if it's 13 centimeters, we have to figure out how far in wavelengths you are if you move. We said we moved from 0.1 or 1.1 to 1.8, so it's 0.7 centimeters. So our delta wavelength that we're actually going to be worried about is going to be taking 0.7 over, and this is, wait a second, is that? Tell you what, it'll be easier to do it this way, I think. It'll give you a little more resolution, I think. Let's move from right. We know if we're right here, the voltage maximum seems to come square on about 5 centimeters. Can you see that? Class? It's pretty much right on 5 centimeters, isn't it, right here? If you look, everybody seeing what I'm saying?
Yeah.
Let's use the voltage maximum, not minimum, because the minimum is at an odd place. So I know if I'm at a voltage maximum here, now think about it. When I'm at the voltage maximum, right here, I'm going to move from here to the load, which is right here. So how far am I going to move? Well, let's see. I'm going to move, it's 5 right here, and this is 1.1. So that's going to be 3.9 centimeters, isn't it, class? Y'all agree with me? Just think about that. That point is at 5. The load we know is at 1.1. The difference would be 3.9 centimeters. Thumbs up or something so I can know you get that. Everybody? Okay. So it's 3.9 centimeters. Now I have to figure out how many wavelengths that is. So the actual delta lambda I have to move would be equal to 3.9 centimeters divided by 13 centimeters. And what's that in terms of a wave? That I'm not sure of, but I can do a calculation, hopefully. When I put that over here, I get 3.9 divided by 13, and that equals 0.3. Good. So I know I have to move 0.3 lambda to get to the load. Do you all agree with that? All right, here's the deal. We go from the voltage maximum right here, right there. Oops. Let me say it this way. We're going to go from, and I'll use this cursor. I hope you, can you all see the cursor on the screen?
Yes.
From the voltage maximum right here, and we're going to move it to the load right here. We're going to go a total distance of 0.3, right? Isn't that right? 0.3 lambda, correct? So follow me on this. Here we are. But now we're not moving towards the actual generator. We're moving from a point to the actual load, right? You with me on this? We're not rotating in wavelengths towards generator. We're going to go the other way. Here we can see the measurement is 0.25, right? Now you can use the circle underneath that, and that one has wavelengths. If you look here, wavelengths towards load. Can you all see that on your Smith chart?
Sure.
Now the only reason I'm doing this is because it makes it easier in terms of the mile markers. Now, what does the mile markers say here if you go to the inner one? Doesn't it say 0.025? Right? Can you see it just inside? There's the outer 0.025. On the inner one, it will be 0.25 as well. Do you all see that?
Yes, sir.
Now I have to add 0.3 to that. So when I add 0.3 to 0.25, I get 0.55, don't I? Right? 0.25 is where I start. I'm going to move a third of a wavelength, which is 0.3 lambda. So when I add 0.3 to 0.25, I get 0.55, correct? Now, what's the golden rule? Anytime you get more than a half wavelength, what do?
Subtract the wavelength.
Right, half wavelength.
Or half wavelength.
So we subtract a half wavelength and I get 0.05, right? How many understand that, right? The distance I'm going to move, if I look here, if I add 0.25 plus 0.3, that's the distance I have to move, I get 0.55. Now that is beyond a half wavelength. So then I subtract a half wavelength, and now I know I need the mile marker 0.55 0.05, and this is on wavelengths towards load, not generator. That's the inner one. So I look over here, and I hope you can see this. Let me try to blow this up, magnify it. Give me 1 second. Now I'm going to use this cursor. Go use yours, and you see this is now your wavelengths towards load. And here it's 0.0, and that 0.04, that's I think 0.05, isn't it on yours?
Yes.
I'm gonna look this up. Right here. Right here. Can you all locate that point on yours? Remember, it's on the inner one, 0.05. You all see that, class?
Yes.
So now I take my straight edge and I draw a line through there from the center of the circle through here. Just draw with me. And this is an approximation, but it's a good way to do it. And just, you don't even have to draw a line through everything. Just mark that point right here. Remember, we got the radius from the standing wave ratio of this circle. This is the normalized impedance. Now you're going to read a value here. I want to see what you guys get. Mine's a little messy, but on this circle right here, I'm getting about a real part of about 0.5. Check yours. Do you get 0.5 as the real part? You get it, everybody?
Yes.
And for the imaginary part, what do you get?
Minus 0.25.
About that, somewhere in there. I'm using a black pen. So it's about 0.2 minus J. So this would be, the normalized impedance would be equal to 0.5 minus J, and it looks like it's 0.25. Remember, it's minus because we're below the equator. I like to talk about it that way. When we're down here, the values of J will be minus, all right? When you're looking at this value or this value, these are all negative J. Are you with me? And anything up here will be positive J where it intersects. How many understand that, class? If you did the homework, you got this, right? Now, once we have this, that's the normalized impedance. If we want the actual impedance, what do we do? Come on, guys. Say it again, Tyler.
Multiply by Z naught.
Yeah, and Z naught's 50, right? Isn't that right? So this is going to be what? 25 minus J, and this is going to be what? 12.5, right? Y'all agree with that, class? Now, what does he have in the book for an answer? I think I gave you the solutions to all these, but can anybody tell me? Tyler, you asked me, didn't you?
Yes, sir. I didn't see an answer in the OneNote at least.
Wait a second, should be. Let me, give me 1 second. Where's my OneNote? Hey, those things are supposed to be there. Tell you what, I'll get this for you right now. I'm very sorry about that, but there should have been. I know the solutions are available everywhere, but the solution should be, this is chapter 2. Matter of fact, what I'll do is this. I'll just pull all of chapter 2 solutions right here for you. That way you got them all right? And you can go and take a look at that. But I'm kind of curious what he says for that now that we've got the answer and we worked it. That's 31, right? Class,
Yes, sir.
Yes, sir.
I'm just gonna click it. What problem is this? Knock it back a little. So what did we get? We got our wavelength estimate is 13. He has 12.6. The Viswar is 2. And he got 0.55 minus J 0.25. We had 0.5 minus J 0.25. That's just, you know, it has to do with how careful, or really how resolved your actual drawing instruments are and eyes is that. But you all see this, class? That's how you do it. With me? How many see this right here? Now this is a good problem because it makes you think. It's not just, you know, you got an equation and calculate. You have to think through the problem to do this one. And you got the solution. Everybody got that? Thank you for that question. It was a great way to lead into this lecture.
Thank you.
Sure. No, I mean, it was a great question. But y'all understand it now, class? All right, let me continue with matching now. I want to go through both shunt and series matching. From last time, did anybody have any questions at all about the homework with using a series or a shunt element? What I'm going to do is do shunt stub. I'm going to do a problem with a shunt stub tuner with a, let me restate that. I'm going to do a problem that will require us to put something in parallel or shunt. That's the term that means parallel. And give me 1 second.
And Professor, Professor,
Yeah,
the term stub means when we use like a transmission line instead of an actual like capacitor or inductor, correct?
exactly. And you have your Smith charts, but I want to take you through, this is going to be what's called shunt tuning or stub tuning, depending if you use an actual component or if you use a transmission line. So I'll try to do this as clearly as I can, and I want to make sure you see this. All right. Now, last time what we did is we had a transmission line, right? And we had some ZL here. We had some Z0. And we first found ZL, right? And that was capital ZL over Z0. Then the second thing is we moved until we had the Z in, the normalized input impedance is 1 plus J plus or minus JX, right? Remember this? That was the key. And so we're moving until now we get an input impedance. This is still a normalized impedance right here to be whatever this distance is, it'll end up being an impedance of, and I'm looking here, of Zn, normalized Zn, equal to 1 plus or minus JB, right? And then the next step was to get rid of the minus JB. That would be a normalized impedance. And we add an element. We always add an element so that we get this. we're going to have, if it's plus JB, you're going to add minus JB, an element, whatever that is, in series. This is still impedance. Here's the length of the line, and here's your normalized, or here's your load, and this is Z naught. This length is determined by the fact that the Zn at this point would be 1 plus JB. Now, that's an impedance, correct, class? That's a normalized impedance. So when I do this, what circuit element has a negative sense, a negative J sense to it, class? Anyway.
A capacitor.
Capacitor. Capacitor has, now I'm just going to show you how to do this. If you have minus JB there, well, minus JB is a normalized impedance, right? So we could multiply that by Z naught to get the actual impedance we want to get rid of, I mean the reactance. Or we could just leave it as normalized, and we could say, well, capacitor has an impedance of minus J over omega C, and if it's normalized, it's divided by Z naught, isn't it, class? How many see that? Right? Let me make sure that you guys see it. And guys, if you can turn on your cameras, it helps me, please. Anthony and Haran, I'd appreciate it. If you can't, or if there's some problem, I understand, but it helps me. You all see this now? I can tell by the shaking of the heads. Okay. Now, we can get rid of J, but you can see the value of C is determined by what? It's just 1 over what? Omega Z naught, right? Agreed? If we wanted to put an inductor in there, well, what we'd have to go is not to the point where we have 1 plus JB, but 1 minus JB, correct? We'd have to move a different length, right? We have to go to the point where it's 1 minus JB. Everybody clear with that?
Doesn't the B need to go in the denominator of the capacitance equation?
Oh, yeah, it does, actually. I'm getting
Okay, thank you.
ahead of myself. But if this is the right equation, we put the B down here. I'm sorry about that. You're right. And that is normalized, remember. You don't have to do it with normalized, but the book, I think, does it. Now, if you wanted to use an inductor, you would move until you had an input of 1 minus JB, correct? And then you would put a normalized inductance value that would give you plus JB equal to J omega L over Z naught. And I'm going to leave it there. I think we all, does everybody got that? That's series impedance, right? Now, if we do shunt impedances, here's what happens. It's different. Now we work in the admittance domain. So our steps are, this is going to be a shunt, and here's what I mean by that. Here's are going to be our typical transmission line. This is going to be ZL here. Some characteristic impedance Z naught. I know I'm going to go to a distance where I have, and I've got to do this the right way. So we start by saying we get ZL is equal to ZL over Z naught. That's our first step. Right after that, we get YL, normalized admittance, as 1 over ZL, and that's simply equal to Z naught over ZL. Y'all follow me? Now this point is the one that we're actually going to move from. And I'm going to show you on the screen. For instance, if I had I'm going to assume just for now, my ZL normalized is 1 plus J. So if I have 1 plus J, it's right here. That would be 0.1, and it would be ZL equals 1 plus J1. Can you all see that? I'm trying to just show you. It's a little messy. Are you with me? Now, if I take this compass, like this, and I take this, my straight edge, you don't have to do it this way. You can just actually calculate the value and plot and point. But if you take this and go right through to this point right here and make a mark right here, this is YL. It's 1 over ZL. So that would be 0.1. This would be 0.2. Are you with me, everyone? Now remember, we're in the admittance domain. Everybody got that? Now listen. Now you're going to move along this circle until you hit either this point right here, I'll call that 0.3, or keep moving and hit this point right here, where it would be 1, and it should be minus J1 right here. This would be 0.4. Either one of these 2 points you're going to move to. So you need to move from here all the way around to here if you want a minus J1 to get rid of. So I'd move from here, I'd go all the way around and come to here. And I want to do this one for you to show you. So let's figure out first how far we move. Now, the reason is that I got a 1 there, right? So the next step, once I move this far, is I'm going to add an element in parallel or shunt that will get rid of this minus J1. And the element that has a plus J sense to it in the admittance domain is a capacitor. We're going to deal with that in 1 second. But first, let's figure out how far we move. So if you look here.
How do we get scooted?
Yeah.
I was going to ask if you could scoot it up. Okay. Thank you.
Sure. Yeah. I'm looking at this and that to see how you're doing. And unfortunately, sometimes I assume the screen's okay. All right, so I'm moving from here all the way around to right here is what I'm saying. So what do you read as this mile marker? Can anybody tell me? On yours? It's wavelengths towards generator now. What are you getting? I got 0.338. No, wait a second. 0.42, 0.41. Is that 1.45? Is that about where you're getting, guys? Anybody tell me? This is on the outer rim. No, I mean 0.405. I'm sorry, 0.405. Do you get about that, class? Take a look at yours. John, do you get that? And Caleb? And Carlin, do you get that? Can you all see it? You don't? Can you see where you can see where I'm at here, where that cursor is, right?
Yes, sir.
You all see the cursor? I mean, look on your Smith chart. What value do you get there? And that's just a straight line from the center through that point to right here. You could literally take a straight line and go right from here through there, through this point, right out the other way. Can't hear you. Turn on your mic. Can y'all? I can't hear. Can you hear? You're on. You got to enable your mic. There should be a little microphone thing on your computer that I'll just show you. If you look over on, try to show you at least. If you look on my computer, oh boy. You see where it has mic? You have to enable the microphone.
I think I have it.
What's that?
Is it like 0.405?
05.
Okay.
Yeah, about that. You guys got that? You see it now, Carla? You're muted. Here, let me unmute you. Okay, go ahead. Still can't hear. Can anybody hear her?
I can't.
Okay. How about this? Do you understand it or not? I mean, do you get that or not? Okay, go ahead, talk. Can you hear her or no? I can't hear her.
I can't hear.
You can hear her?
I can't.
Okay, I can't either. Hold on. Well, in chat,
She just shouted, "Where is the 0.2 coming from?"
the 0.2, there is no 0.2. It's 0.405.
I think she's talking about 0.2 on the actual Smith, the point that you have labeled.
Oh, 0.2. This is simply 1 over ZL. This was ZL, right? This is 1 over ZL. And where you get it, if you want to get it this way, you can take a straight line, and this is messy, so bear with me, and go right from the center of the circle through that point. This is not going to be a nice one, but when you draw a straight line here, this is ZL, and the conjugate point here will be 1 over ZL or YL. Can you all see that? It's always 180 degrees around the circle is YL. That's just the characteristic of the Smith chart. Now, you should be able to see something here that's about 0.405, and it could be a little bit off, but can you all see that?
Yeah, I got 0.404.
That's fine. It's close enough. Are you with me on that, class? Now, that's the admittance domain, right? We want to move from here to here. So what we're going to do, hold on. What we're going to do is find out what this mile marker is right here. What do you guys get for that one in yours? You tell me. Is it 0.334?
I got 0.338, but
Yeah, that's what I got as well.
338? All right, something like that. All right, agreed? Something like that. Now, hang on. I got to let my dog out. Hold on. What are you doing? You want to go out? Go ahead. Anyway, getting back to this, how far did we go from here to here? I mean, if we went all the way around, it would be half wavelength, right? So it's close to a half wavelength. So I take this 0.338 and I subtract 0.405 from it, right? You agree with that? I take the point where I went to, which is 0.338, pardon me, and I subtract 0.405. What do you get for that? Anyone? I think I can write right on here. Class?
minus 0.67 for me.
All right, minus 0.66.
0.067.
0.67. What do we have to do?
Add 0.5.
Right, and what do you get once you do that?
0.433.
All right, so that means I'm just about a half wavelength. That means when I move for that problem, I had the normalized impedance equal to 1 plus J1, right? And when I take 1 over that, I get what? Do I get 0.5 minus J 0.5? You can check me on that, right? I think it's about right. Isn't it, class?
That's right.
All right. Now I've moved a distance of L equals, what was it again? 0.4 what? Anyone?
0.405.
Mm,
What did you ask? I'm sorry.
I want the total length I moved. So it's 0.33, it's 0.405, I mean 0.338 minus 0.405 plus 0.5. What do you get?
0.433. But you're on MathCAD right now.
Thank you. So I'm sorry about that. I move a distance of 0.433, you said? Right? Didn't you just say that? Somebody said, Ben or Tyler? Is that right? Or John? Y'all got me? Now, at this point, what is the input impedance? Isn't it 1 minus J1 right here? Right? We moved from here. First, this is our input impedance we came in at, 1 plus J1. We took 1 over that, we get 0.5 minus J0.5, right? Now we move until we get an, not impedance, admittance of 1 minus J1, right? How many see that? All right. We got to get rid of this, right? So when you think about this to get rid of it, here's how I'm going to do it. I know that the capacitive reactance, I'll call it X sub C, is minus J over omega C, or really 1 over J omega C, correct? Y'all with me on that? I'm making sure everybody sees that, right? That's the capacity, that's the reactance of any capacitor. It's got a J sense to it, right? Minus J sense. Now, if I take 1 over that, 1 over X sub C, that's really the capacitive admittance. That's capital Y sub C, or that would be J omega C. All right. Now, when you normalize it, if you were in the impedance domain, you would divide by the characteristic impedance. When you're in the admittance domain, you multiply by the impedance. So then I get normalized Y sub C is equal to J omega C times Z naught. Does this make sense to everybody? Everybody with me on that? Now, why did I do that? Because I want this to be equal to the minus, the minus J1. Remember, we've moved to this point. We have 1 minus J1. We want to get rid of that minus J1, so the input admittance is just 1, because that means the input impedance is 1 as well. 1 over 1 is 1, right? And if the input impedance normalized as 1, then the actual input impedance is Z naught, and we've got matching. There's the input impedance is the characteristic impedance of the line. There's no reflection. So what we do is take J1 is equal to J omega C times Z naught, or we can say simply that the capacitance would be 1 over omega Z naught. Now that's using a parallel method, and that means, or a shunt method, and that means the capacitor would actually go here in parallel with the line at that distance. And this would be the value of the capacitor right here. Not in series, but in parallel. Do you all see that, class? That's shunt. The word, whenever you hear shunt, it means in parallel. And it's important you understand that. And by the way, shunt stub or shunt tuning is used much more frequently than series tuning for a lot of reasons. Because with a shunt stub tuning thing, it doesn't have to take all the current through the line. If you put a series inductor, for instance, it does, or series capacitor. All the current and signal goes through the component. This doesn't. This only takes a small fragment of that. You got me on that, class? All right. Now, how do we do this same thing with a transmission line, right? And how do we replace this component with an actual length of line? And what we're going to do is get something like this. You know, I burned through these pads so fast. I wanted to get the yellow pad, but we'll use the white one for now. So how do we do it with a transmission line? Just pay attention to this. You don't need to take notes. I just want you to watch this, and I can help you make sense of this mess. All right. Now, there's 2 ways to do this. First, when we take a look at a transmission line, here's the load. We make that load either a short or an open. I'm going to do this with a short-circuited load. So now my transmission line looks like this. And ZL equals 0. And this is still Z naught. Everybody with me? Now, when I look at this, when I look at the input impedance, Zn here, I want you to follow me. Zn is always equal to Z naught, right? Times ZL, right? But ZL 0, correct, class? So you don't need to write it. Plus JZ naught times the tangent of beta L over, and if you think about it, what comes next down here? Well, let me write the equation for you. Zn is equal to Z naught, right? Then it's times ZL plus J times Z naught tangent of beta L over Z naught, right, plus J times ZL tangent of beta L, correct? Right? I just rewrote the, well, if ZL here and here is 0, then it just means I divide this by Z naught, or I get an input impedance that's really equal to just J Z naught times the tangent of beta L. Do you all see that? That's the input impedance. When it's normalized, the normalized input impedance of that shorted load would be equal to just J times the tangent of beta L. Now, the tangent itself can have a value that goes from plus to minus infinity, and it goes through 0, if you know what a tangent is. And what it really means is this, and I hope you appreciate this. When I'm talking about, I don't have a clean Smith chart here, I just used a bunch. When I'm talking about the input impedance of a short-circuited transmission line, you know, when you're at the load, if it's short-circuited, what's the impedance? If it's a short, anybody?
0.
0, right? That's the definition of a short circuit. It's 0 ohms. So where's 0 ohms on here? It's right here. Can you see that? See that right here? That's 0, right? That's, if you look here, all these, like these are the R equals 1, R equals 0.5, then that's R equals 0.2, going down, down, down. Finally, at the outer rim, R is 0, and when I'm right here, J is 0. So that's where the short is. And you can put down the impedance domain, that's a short. I come in here. Now, if I want to get rid of something in series, say a plus JB, right? Or a minus JB, I move around here on the outer rim, and you can see the values here. That's 0.2, that's J.2, J.3, J.4, so forth. There's J1, and so forth. You move until you get the right normalized input impedance that you want. Do you all see that, class? And if you wanted to get J1, for instance, you wanted to move here, you would move from 0 to this point, and that would be 1/8 of a wavelength. All right, you can check that. I know if I move all the way around here, it's a half wavelength. If I move a quarter of the way, it would be 1/8 of a wavelength. All right. And that's the basis of impedance matching with a series stub. So I'm trying to cover this in the time, and I'm already over it. If you had a series stub and you were doing impedance matching, what would happen is this. Let's assume I get the right value here. I have Z in here, right, equal to 1 plus JB, and this is going to be my Z in. Then what I do, if it's in series, I would put a short circuit stub like that, where the input impedance of that short circuit stub would be minus JB. And that's normalized. And that's how you do it with a series shunt. Does that make sense to everybody, class? Give me a thumbs up or some way, shake your head if you understand it. Are y'all with me on this, class? That's series. Now, if we wanted to do it in shunt or parallel, what we do is this, and I'm going to put it down here. We take the same thing, same equation, that's CL, and this is Z naught. So then we'd get normalized input. Here, my ZL is going to be 0, or it's a short circuit. And let me get another piece of paper. I don't mean to try to rush, but I see time flies when you're using Zoom. If I go ahead and I put a short circuit here, it's a short. I know my normalized input impedance is 0. I know my normalized input admittance is infinity, right?
Could you skip down a little bit?
Yeah, I'm sorry about that. What I'm really saying is that if I have a short circuit, right, I know the normalized impedance would be 0, correct? And the normalized admittance would be infinity, right? Everybody with me on that? Now, if I have a normalized admittance of infinity, that's this point right here. That's infinite, and that's an admittance of infinity. That would be at the load. When you have a short circuit stub and you're looking in the admittance domain, you start right here. Now we're going to put this in parallel, right? So suppose your input admittance was 1 plus JB. Can you all imagine that in your mind? I would want to add a minus JB, correct? Let's give it a real value. Suppose the value of the input admittance was 1 plus J1. Y'all with me? I'm keeping the numbers simple. I would want to move from this point until I hit minus J1. And where is that? Can you all see that this point would be minus J1 here, class? How many see that?
You skip it down.
Yeah, I'm sorry about that. This point here would be minus J1. I would move from here to here, and I would move, if I wanted J1, a distance of lambda. How far would that be? It's a quarter of a circle, so it's lambda over 8, because I know if I move all the way around, it's a half wavelength, halfway around a quarter wavelength, a quarter wave around an eighth wavelength, right? So, with me? I'm just arbitrarily choosing a value of J1. I've got to get rid of, I add minus J1, but it's in shunt. So it would look like this. Now you would have a stub that's shorted here, and the length of this would be actually L. Dr. Wentworth likes to call it L through. And this would be the length of the stub. And then this would accomplish matching as well. And again, the key thing is, be it either shunt or series, is always moving from the load till you get the point where you have 1 plus J, plus or minus something if it's impedance. If it's admittance, 1 plus J something, plus or minus JB, right? And then adding a component that will get rid of that JB or JX, correct? In series or parallel. Everybody with me, class? I'm going to give you a bunch of problems, and so you got the solutions. So hopefully, can somebody check and see if they can read the solutions, just for my sake? You can read them? Go ahead.
I was going to ask you if you could scoot it down one more time. I'm sorry.
No, let me know. Anytime you can't see, just let me know. I'm just showing you how the connection would look like. And this is in Dr. Wentworth's book. He shows this. I can even show you where it is. I would like, if you don't mind, I know I'm losing people. How many people do we have here besides me right now?
8.
8 people. So we've got some people that already signed off or never showed up, but that's okay. It happens. So this is, by the way, what he's showing you here on page 86. Come on. Okay. On page 86, this is an open stub tuner. All right. Opens aren't usually used. Usually it's short circuit. And the reason is, if you have an open stub here, there's a plus and minus voltage. There's an electric field that's right around there that can actually influence components nearby. So they normally put a short circuit on stubs, almost always. I've not seen an open circuit stub tuning, but they probably exist. And this is short circuit stub tuning on page 85. And it's just putting a short, and what it looks like really is this. You're putting an impedance in parallel with, or an admittance in parallel with the actual line admittance at the point where you get 1 plus J something. Agreed, class? Now, you got, you got the solutions to these. Could somebody check and make sure you can access the solutions on OneNote for me while I got you all here?
I just tried to open them and I actually wasn't able to read it. The
All right,
file wasn't open.
let me see what the problem is. All right, if you highlight that and you right click on it, let's see. Let me see if I can do this. They're there.
I was able to right click and save as, and it downloaded.
Save as what? Just something else?
You just right click save as, and it downloaded automatically.
Could you try that, Ben?
I just tried it. It's telling me I can't open the page. Maybe if I try something else, it'll work.
Well, could you guys right now just go to OneNote and see if you can open the solution? Because I've had trouble with this with other people. I didn't want to put all the pages in there because it takes too long. But if I put it in as a link and you right click and save as something.
I was able to open it.
You were?
Yes, sir.
Ben, do you have a Mac?
I do have a Mac. Maybe it's just me.
No, there's usually tricks to this. Anybody else with a Mac computer? An Apple product? Look, I can forward it to you. I can email this thing to you.
Okay, thank you.
Matter of fact, let me do this too. I'll email everybody. It should come up, I hope. All right, hold on. And this is going to be to, hopefully this will get to everybody in a second. And you can use that then. That should be all of them. Now, what I wanted to do is just basically tell you that with impedance matching, we're going to do these problems. And then we're going to go through transients on Friday. Okay. I'll tell you a problem I'd like you to try. Do y'all have fresh Smith charts or not? You need a compass. That's a compass. And you need a Smith chart and a straight edge. Now, how many have Smith charts right now? Just jump. 1, 2, 3, 4, 5. Everybody, if you can, I'm going to pick a problem for you to do. And you can look at the answer, but don't look now. Look at problem 240. I want you to do it now while I'm here. 240. And it's a load of 25 plus J90. And it's to be matched, you're to do impedance matching with a parallel or shunt stub tuner that's a short circuit. All right. So get a fresh Smith chart and try that. And I'll tell you the first thing you need to do is normalize the impedance. And then after that, you're going to move in the admittance domain. So then you have to find the normalized admittance of the load. Okay. Those are steps. Yeah.
Dr. Biggins, I was wondering if you could show it, like show the problem on the screen. My book was supposed to come in yesterday, but it hasn't arrived.
Yeah. Here. Wait. Give me 1 second. So this is problem 240. Can you see it?
Yes, sir.
The impedance, the load impedance is 25 plus J90, and the characteristic impedance is 50. Now, what I need to do is I got to print off a few more Smith charts for myself while you guys are doing it. If I can find it. Hey, actually, I might have that. Oh, this is the good Smith chart. I'm going to send you guys this one. This is a really good one. All right, the Smith chart I just sent you is a very large one. It's high res, and if you can print off these copies, you'll be set. I'm going to see if I can print them out. Let's do about 12 copies. Oh. I'll be right back. Hang on. Oh. You guys getting it? Hmm. Um, all this up. I thought this was a good one. You guys, have you got it? People? How many have got it? Are you having questions? Anybody with questions? Anybody? Tyler, did you get it? You got it? Ben, have you got it?
I got it wrong. Looks
Okay. Caleb?
I haven't finished.
All right, this couple, keep working, but I put up the solution on don't look at it. Let me finish it, and then, I mean, if you're done, you got the wrong answer, you can look at it, but it's a classic problem, really.
And Professor, when it asks us, like in this example, it says find the solution. Is that just asking for the length of the stub, really?
It's length of the line that you're going to, with the point you're going to connect the stub, and then length of the stub. There's two parts to it, right? The load on the stub is a short. So you first, I can talk you through this if you can look with me. First thing you have to do is get the normalized impedance, and you should be able to plot it right there. Can you all see this on figure 2.42, class? So once you get the normalized impedance, because this is going to be connected in shunt or parallel, we have to get the normalized admittance, which is right there. You all see it? Now, once we have the normalized admittance, now I've got to move until I hit the point 1 plus j something or 1 minus j something, one of the two, right? Correct, class? Now, he wants to hook up a short circuit stub tuner, right? And here's how you do this. If it's a short circuit stub, it means the impedance is 0, but the admittance is infinite, right? Right? I mean, for the load, correct, class? And if you think about this, the admittance being infinite is right there, correct? So if you got a short circuit stub and I start adding length to it, the values I'm getting are negative j. Can you all see that? It means if I'm up here and I've got, if I land here and I have 1 plus JB, the shortest stub would be one where it would be right here with a short, I mean, if I have a stub, I would want to short it and just move a small distance. Here, the value you see is 1 plus J, what is it? J, I can't even tell you right now.
Like 2.6.
All right. If it's J 2 points plus J 2.6, I move down here until I hit minus J 2.6. And it should be about 0.308 lambda on wavelengths towards generator if you look at your Smith chart, right? And that means you moved from 0.25 to 0.308. And what is that? That's let's see, 25, 30 to 0.05. So it's 0.048. Is that right? Lambda? If you take 0.308 from 0.25, what do you get?
0.058.
0.58, pardon me, 0.058. So that's how far you move, agreed? And then you would connect your shorts. I mean, you're basically gonna move from here to here. So you're gonna move from 0.423 lambda to whatever this point is when you 0.198 lambda. So you take 0.198 minus 0.423 lambda, you're gonna get a negative value. So you have to add a half wavelength. And that's this math right here. So you're gonna move 0.275 lambda from the load to the point you're gonna attach the transmission line. I mean the parallel shunt. And then your actual length of the shunt would be from here to here. And that would be 0.058 lambda. Everybody see that? All right, any question about that? All right, for homework, you're gonna do the rest of them from 2.35 all the way to 2.42. And on Friday, you're gonna get transients. And then you're gonna get a quiz right at the beginning of class, all right? And it'll be on this material. Got it, everyone? I don't know if Carlin stepped away, and I'm not sure if everybody else heard this, but I'll put it in my OneNote, and so I'll put that. There will be a short quiz. At beginning of Friday's class. Now, I'll tell you what I expect you to do is have a compass, a straight edge, and a calculator, of course, and you want to do all your work on the Smith chart and clearly label like point 1, 2, 3, 4, and then draw the circuit out and how the links, you put them right on the circuit, you know, like you draw the transmission, draw the load, then the transmission line, indicate the length it is from the transmission line to the point you're going to connect either the short circuit stub or the element. It might be a capacitor, inductor, and show me a drawing of that either in series or parallel. And remember, shunt is parallel. You all with me on this class? All right, I hope I can do justice to this. How many watched the videos by that lady? Anybody? She does a great job. She really is gifted. And If you have any questions, you can ask me right now.